This is Calculus 12, Chapter 2.3, Part 2. We're going to be looking at continuous functions. And the definition is f is a continuous function on an interval if and only if. It is continuous at every point in the interval. Another definition is a continuous function f is one that is continuous in every point in its domain. Notice this one says f is continuous if and only if, and this one says a continuous function. So small distinctions. It's like being a lawyer. Here's an example. Y equals 1 over x squared is a continuous function because it's continuous on its domain. Its domain is the absolute value of x is greater than 0, even though it's not continuous on negative 2 to 1. This is also the same as x does not equal 0. So it means it's continuous everywhere from x is greater than 0 all the way to the right, and x is less than 0, it's continuous all the way to the left. So here's some theorems. We're not proving all of them. Any polynomial is continuous on all reals. Any rational function is continuous on its domain, that is, anywhere except at NPVs. And the following functions are continuous in their domains. Taking roots, odd roots, x is all reals. Taking even roots, we can only take even roots when the radicand is greater than 0. And note that the functions are continuous on their domains, and that does not imply everywhere. Such as this one. Trig functions, cosine and sine. It's continuous on all reals. Tangent is continuous on all reals, except x cannot equal pi over 2 plus n pi, n being the set of integers. For inverse trig functions, we can say arc cos, we can say inverse cos, they mean the same thing. So the domain for that is 0 to pi. And for arc sine, we have negative pi over 2 to pi over 2. And just a reminder, the square bracket includes the endpoints. A round bracket does not include the endpoints. And we have negative pi over 2 and pi over 2 again. Exponential functions, x is all reals. Log functions, x is greater than 0. And absolute value function, x is all reals. And when we're saying x here, it means x as the parameter. Properties of continuous functions. If f and g are continuous at a and c is a constant, then we have the following functions are also continuous at a. So we can add the two together and they'll still be continuous. We can take the difference and they'll still be continuous. We can do a scalar multiplication and it's continuous. We can multiply the two functions and it's continuous. And we can divide the two functions and it's continuous provided that g of a does not equal 0. Okay, proofs. Again, we're only allowed to modify one side of an equation on a proof, and we show that it can be modified to equal the other side. Now, if we're stuck, we use reverse engineering to figure out the steps. Okay, so here's a proof of one of them, f plus g. Since f and g are continuous, that means we can take the limit. Okay, so because it's continuous, we can use the limit definition of continuity. Therefore, we use therefore a lot, and we can use this symbol, 3 dots in a triangle. Remember, this means f of x plus g of x. This is just a slightly different way of writing it. And these two mean the same thing. Now we can use our limit laws of addition and break these up into 2 limits. Now we can evaluate the limits. And just rewrite the function. So we have this is equal to this. And that's our definition of a continuous function. We have continuity. So we have exactly the same thing for f times g of x. And I've saved you the trouble of writing it out. And you can see that the proof is very similar. Let's look at some more theorems. Composition of functions. If g is continuous at a and f is continuous at g of a, then f of g is a continuous function at a. Okay, so this one's slightly different. We have g of a needs to be continuous. And that brings us to our important theorem, the intermediate value theorem. Suppose that f is continuous on an interval a to b. Let n be any number between f of a and f of b, where f of a does not equal f of b. Then there exists a number c between a and b such that f of c equals n. Okay, with theorems like this, it's very hard to understand just looking at words. It's always best to look at a diagram to see what's going on. So here's the big picture. We have a and b. We have f of a and f of b. Okay, remember a and b's are always our x values, f of a and f of b are always our y values. Now, this function can take on some hills and valleys, doesn't really matter. We can try to make it as complicated as we want. It has to be continuous. Okay, that means we can't have any gaps in here. The theorem says it's continuous. Now, n can be any number between f of a and f of b. So let's just pick an n. So clearly f of a and f of b are not equal. Now it's telling me that I have a solution for this problem because n is between f of a and f of b. So that solution is here, f of c. And c is here, and it's telling me that c is between A and B. So that's telling me that there's a solution exists. It doesn't tell me where the solution is. It just tells me that there's a solution. It doesn't tell me how many solutions. As in this example, we actually have 3 solutions, but all we care is that there's at least one solution. So how do we use this? Prove that there is a root of the equation of this polynomial, and prove that it's between 1 and 2. We let f of x equal the polynomial. We are looking for a solution C between 1 and 2. Such that we use that a lot, so we abbreviate ST. F of C equals 0. Therefore, A equals 1, B equals 2, and N equals 0 in the intermediate value theorem. So F of 1 equals 4 times 1 cubed minus 6, 1 squared plus 3 times 1 minus 2, and that equals negative 1. This is less than 0. And this is n. Recall that that's n. We just stated it. F of 2. 4 of 2 cubed minus 6 times 2 squared plus 3 times 2 minus 2 equals 12. And that is greater than 0. Thus, f of 1 is less than 0 is less than f of 2. And we have to state that f is a polynomial therefore it is continuous. So, by intermediate value theorem, there exists a C in the interval 1 to 2 such that f of C equals 0. And this backwards E means there exists. The problems that you'll solve are not this easy. You have to look at the function or even create the function and specify your A, B, and N. And then you can use the intermediate value theorem. So it's a little trickier than this. You just have to find reasonable values for A, B, N. Show that f of A is bigger than or less than 0, and f of B is bigger than or less than 0, but opposite f of A. And then say that the function is continuous, and then use the intermediate value theorem. And that completes this lesson.